I have a box with mass m that is moving at a speed v0 on a frictionless surface. The box then encounters a rough surface where the coefficient of kinetic friction between the box and the surface is mu k, and the box eventually comes to rest. I'd like to derive an expression for the distance that that box will travel on the rough surface before it comes to rest. In order to do this, I'm going to use conservation of energy. I know that the change in energy of this box must be equal to the work that is done on it. Change in energy is final energy minus initial energy equals W. And so another way of writing that is the initial energy plus whatever work was done to the box must be equal to the final energy. And so we need to determine what type of energy does the box have initially and what type of energy does the box have finally. I'm going to define the height as equal to 0 at the surface of the box. And so initially and finally, the box will not have any gravitational potential energy. And so initially, the gravitational potential energy is equal to 0. The kinetic energy of the box, Ki, is equal to 1/2 times the mass of the box times its initial velocity squared. And for the final energy, the gravitational potential energy is still 0 because it's at the same height, and the final kinetic energy is also 0. So K final is also equal to 0. Next, I need to figure out what would be the expression for the work that's done on the object. Work is equal to the force parallel to the displacement times d, or Fd cosine theta. And I know that the force that is taking energy away from the box, the force that is doing work on the box is friction. And that frictional force will point in the direction opposite the displacement of the object. And so the way that we do this is we say if the displacement of the object is to the right, we have a velocity vector going to the right, and if the frictional force points in the opposite direction as that velocity, then those two vectors are 180 degrees apart. And so the way that I would write the work equation is I would write F times the distance that it moves through, d, times the cosine of 180 degrees. And if you plug cosine of 180 degrees into your calculator, you'll find that's equal to -1. And so the work is minus F times d. And we should expect that because the frictional force is slowing down the box, it's taking energy away from the box, and so the work should be negative. And so I'm going to take this one step further. I'm going to write this as the work is equal to minus mu k times n times d. If we made a free body diagram for this box, we would know that the normal force, which points up, is equal to the weight of the box, which points down. And so I can write this equation for the work done on the box as minus mu k mg times d. And so finally, we're going to take all these expressions that we have and plug them in. I know that really there's only two components that go into my conservation of energy equation, and that is the initial kinetic energy that the box has, the work that was done on the box, and that the final energy is equal to 0. And so I'm going to plug all of that in. The initial energy is 1/2 mv0 squared. The work is minus mu k mg d, and the final energy is equal to 0. And so now what I was attempting to do in this problem was derive an expression for d, which was the distance that the box travels before it comes to rest on that rough surface. And so I'm going to solve this equation for d. First I'm going to add the second term to the right side. So 1/2 mv squared equals mu k m gd, and therefore d is equal to m v squared, v naught squared, divided by mu k mg, and there's also going to be a 2 in the denominator. And so the last step, I suppose, is to see that the m's on the top and the bottom cancel, and so our final expression for d will be v naught squared divided by 2 mu k times g. A couple interesting things that I'd like to point out is, first, the distance that box will travel on the rough surface does not depend on the mass of the box. And then also the dependence on the variables that it does depend on. So if I were to have the box moving with twice the initial speed, since the relationship between d and the initial speed is a squared relationship, d is proportional to v naught squared. If it were traveling with twice the initial speed, then it would travel 4 times as far on the rough surface. The only other variable that it depends on besides the acceleration due to gravity is the coefficient between the surface and the block, which makes sense. In this next example, I have a box with mass m that has compressed a spring with spring constant k a distance d. And so the box is being held back at rest and compressing that spring. When the box is let go, the spring exerts a force on the box and shoots it to the right. It travels along a frictionless surface, and then it encounters the inclined plane, which is also frictionless, and travels a length L up that inclined plane. And what I'd like to do is derive an expression for L, the length that it travels up that incline. And so once again, we're going to do this by conservation of energy. So the change in energy is equal to the work that's done on the object. Since the surface is frictionless, actually the work done on the box is going to be 0. And so the change in energy is equal to 0, or the final energy minus the initial energy is equal to 0. And so whatever energy the box has initially, the box will have that same amount of energy finally, because there's no work being done on the box. And so we just need to determine what those expressions are. First, I'm going to define in the picture here that the place where h is equal to 0 will be the level section of track on the left. And so I'm going to call the initial position the height 0, and so initially the box will not have any gravitational potential energy. And so UG initially is equal to 0. The kinetic energy initially is also equal to 0. It's just at rest with the spring compressed. The elastic potential energy, however, is not 0. The form of the equation for elastic potential energy is 1/2 kx squared. And in this case, the distance that the spring is compressed is expressed as a capital letter D. So I'm going to write 1/2 k d squared. And so that's all we have for the initial energy. For the final energy, the kinetic energy is 0. So K final is equal to 0. The elastic potential energy is also 0 because the spring is not compressed anymore. The box is all the way on the right. But the gravitational potential energy is not equal to 0 because now the box is at some height, up here. And so we need to figure out what that height is. If the length that the box traveled along the incline is L, then we could draw a triangle where the hypotenuse is L, and the height of that triangle could be expressed in terms of L and theta. And so the red vertical line that I've drawn is the height that we want. And that height is equal to L sine theta. Because I've drawn a right triangle where the height is L sine theta and the hypotenuse is L. So the length that the box travels along that incline is L, and the height that it will have after it travels that length is L sine theta. And so the generic expression for gravitational potential energy is just mgh, but here the height is L sine theta. So I'm going to write mg L sine theta. And that's critical because I'm trying to derive an expression for the length that it travels along that incline, and so I need to include L in one of my expressions for the energy. And so when I plug these into my law of conservation of energy equation, the initial energy is just 1/2 kd squared, and the final energy is mg L sine theta. So 1/2 kd squared is equal to mg L sine theta. And so the last thing I need to do is solve this for L. L is equal to k times d squared divided by 2 times m times g times sine theta. Here the length that the box travels along that incline does depend on the mass of the box, but it also depends most prominently on the compression of the spring. So if I were to double the compression of the spring due to the relationship between the two variables, which is that L is proportional to d squared, if I double the compression of the spring, then the length that it would travel on that incline would be 4 times as big. L also depends on the spring constant and the angle and the acceleration due to gravity, which all makes sense.